So welcome everyone. This is our first Sim Summit seminar where the speaker is not HapTH but Conrad Matt, so it's very exciting. And we have Apoorv from actually Stockholm who will talk about topological holography. Please take it away. And for those of you who are actually new to the seminar, we try to be as informal as possible, so please ask as many questions. I think just unmute yourself.
Yeah, please feel free to ask and interrupt me whenever you want. So thanks for the invitation, firstly. So I want to talk about an upcoming work, which will hopefully be up within the next month. And this is work that is done in collaboration with Farooq at McGill and Haider at Kent. So the kind of question we want to try to ask is, so we're trying to develop a framework that will aid in organizing the space of d-dimensional symmetric quantum systems. And there seems to be a systematic way to at least talk about symmetric systems where the symmetry is a zero-form finite abelian group symmetry. The kinds of questions we are interested in: what are the gap phases realized? What are fundamental excitations within each phase? Are there some universal properties of transitions that can be extracted just by studying the symmetry structure? Are there some dualities between different phases and different some kind of a map on the parameter space of the theory that helps us, if we understand one corner of the phase diagram, helps us flesh out details about the other corner of some other corner of the phase diagram, which may be related by a duality map. And in order to organize our understanding about these questions, we want to use d+1 dimensional topological order. So the plan for my talk is as follows. I'll briefly describe the framework. I'll try to illustrate the framework by one trivial example, then go into some more details by one slightly less trivial example, and then finally finish off by mentioning a few applications and some directions we could take this in the future. Okay. So more concretely, the setting is as follows. I'm imagining some kind of a lattice which admits a tensor decomposition, whose Hilbert space admits a tensor decomposition. There's a non-anomalous global symmetry G, and the symmetry operator also decomposes into tensor product of local operators acting on site. Of course, these operators satisfy group composition rules. The space of local operators, because this global symmetry can be decomposed into representation spaces of the global symmetry. And the kind of question we have in mind is, imagine the space of all the symmetric operators, which are basically some operators that act on regions with finite support. And these are symmetric, so it's local symmetric operators. So you can imagine something that acts on, say, n sites on some spin chain. And generally it could take this form, but symmetry imposes that the product of the representations on each site must compose to the trivial representation of the group. So we want to explore some kind of space of Hamiltonians that are generated by these kind of deformations, and try to maybe systematize the phase space. And so something that's useful is, of course, this modern perspective on symmetry, where symmetry operators are essentially topological subsector of operators in some quantum theory, basically because we can deform them within correlation functions topologically without changing what answer one gets when one computes a correlation function. And these operators, well, I think this slide is very familiar to most people in the audience, but I'll still go over it. You can take operators, and if you have two operators sufficiently close by without any insertion in the middle, you can replace it by just a single operator that is read off from a group composition property. The action of symmetry operators on local operators is also topological in the sense that is given by linking, and the phase one picks up when a symmetry operator pierces a charge is basically read off from the representation that leaves the charge. So this kind of a perspective on symmetries as topological operators has further generated a number of generalizations which involve keeping in mind operators that symmetry operators that are defined on higher codimension submanifolds of space-time act on higher dimensional charges. For example, line-like operators acting on line-like operators in 3D. And also more recently, there's been a lot of interest in operators that don't satisfy group composition, but satisfy something more general, the fusion algebra. So I think summary of current state of understanding of symmetry is that it's described by some kind of a higher fusion category of topological operators within a sub-algebra of operators within a quantum field theory. So kind of more broadly speaking, the kind of thing that we would like to do, which maybe is the first step towards or a small step towards, is you take a d-dimensional theory with some symmetry category C and try to use d plus one dimensional topological order that's constructed from the center of C. So it takes in the same input data as a symmetry category, and use the bulk or the higher dimensional TQFT to try and organize some understanding about the phase diagram, phase space of the d-dimensional theory. So let's restrict ourselves to these finite abelian groups in category vec G. Right? So in this case, it's kind of a dictionary between different things on the d-dimensional quantum system side and the topological order side. If you given a quantum system with G symmetry, you just construct a Dirac fitting theory or a topological gauge theory with that global symmetry as an input. And the reason for doing so is basically because zero form symmetry on the boundary. So the topological gauge theory has a G one form symmetry. And that restricts to some symmetry operators on the boundary. But so the symmetry operators on the d-dimensional quantum field theory map to magnetic surfaces of the topological order that are d minus one dimensional, restricted to the boundary, generate the global symmetry. The bulk also has charged line operators, endpoints of which become charges that carry non-trivial representation on the boundary. So they serve the role, for example, of order parameter for symmetry breaking. Gap boundaries and gap phases are labeled by the same data. So there's a kind of isomorphism between the set of gap boundaries and gap phases. And zero form symmetries of the bulk become something like minus one form symmetries of the boundary. So they act like dualities. They permute. They act like some automorphism on the phase space of the d-dimensional theory. So they can map between different gap phases or map from one critical point to another critical point, things like that. So actually, the main thing that we want to use are these zero form symmetries on the. You can see my cursor, right? Yeah. Yes.
Yeah.
So the main thing that we'll actually use most are these zero form symmetries, which become dualities on the boundary. So our strategy is going to be to actually try to understand some corner of the phase diagram, or actually use knowledge of some corner of the phase diagram and a duality to understand some other corner of the phase diagram. In principle, if one has an anomalous quantum system or wants to study downstates or phases realized in an anomalous quantum system, that can also be dealt with by just including a non-trivial topological action for the Dirac-Grafton theory in the bulk. And from a condensed matter perspective, these anomalies sometimes manifest in some lower constraints on the ground state called Lipschutz Mattis constraints. So yeah, there are various contexts in which we might be interested in studying anomalous quantum systems.
This D plus one dimensional theory is attached to any such D-dimensional theory having a symmetry, or you're considering a system which has both D plus one and D-dimensional parts?
So I'm thinking of the D plus one theory as a theoretical tool. I'm really interested in the D-dimensional quantum system, understanding the phase diagram of that. But I just use. I just want to study D-dimensional systems. Physical.
So should I think of this D plus one dimensional theory as physical attached to the D-dimensional theory, or just
no,
not
okay, physical. Thanks. Just a kind of organizing tool, not should assign a physical meaning to D plus one dimensional bulk.
Okay, thanks.
So
I also have a question.
Yeah.
So there are some topological order whose there are some topological order like some graded category that has but in your picture, I'm just
I'm sure.
I don't think so. In that case, yeah.
Okay. Yeah. So I'm only considering theories that have gap boundaries, and so there could be some microscopic quantum system associated with its edge. If you consider, for example, Reshethikin or John Simon's theory, then I think the edge does not have well-defined microscopic Hilbert space. There's some gravitational anomaly.
Right.
So like I can't kind of UV regulate that theory or really put it on a lattice. But I'm considering, so at the end of the day, I want to ask what can I say about microscopic spin chains or lattice models with some global symmetry. And this is a complicated question, so I want to have some kind of clean perspective on it. So that's where it is. But, yeah.
Okay.
Yeah. So let me first talk a little bit about the topological gauge theory and mention the ingredients that would be useful for us. So there's some finite group G. It serves as the input of this theory. The line operators or the one-form symmetries in the case where G is abelian are basically labeled by tuple elements in the tuple G and rep G. G are basically the flux lines of this gauge theory, and rep G are the charges. So it's G squared for an abelian group. And the topological correlations are basically encoded in the pairing of a group element with the representation. So the S matrix and the twist, this D should not be here, sorry. The twist are both basically captured in this alpha of G. Zero form symmetries of these of Dirac-Grafton theory are basically some subgroup of automorphisms of the A of G, which are the lines which preserve alpha. And together, the zero form and one form symmetries form a two group, which won't be terribly important for what follows, but it's just the structure. So these two things will be important, A of G and D of G. And
do you have a non-trivial Pasnikov class as well for the two group?
No,
Okay, so just an action.
just an action. Yes.
Okay, thanks.
And oh, sorry, I think there was supposed to be another slide here, which okay, somehow I seem to have deleted the slide. Sorry. Well, so the action of these operators, these different line operators in surface, the zero form surface operators in the boundary, are basically given as follows. The flux operator, which is labeled by group element, becomes a symmetry operator on the boundary. A pure charge or a pure charge line becomes an operator on the boundary that measures the G-twisted boundary conditions if it wraps the spatial cycle. If they wrap the time cycle, the pure flux operator measures or implements G-twisted boundary conditions on the 1D theory. And a pure charge line wrapping the time cycle basically changes the symmetry eigensector of the theory. Lines that end on the boundary serve as order parameter for symmetry breaking because it inserts a non-trivial operator that transforms in a non-trivial representation of the symmetry group. And the zero form symmetries of the bulk basically become -1 form symmetry operator, or duality. They implement a duality on the boundary. So they map between different points in the phase space. Now, another piece of data that would be useful for me is the set of gap boundaries of these Dirac-Fitting theories. And these are labeled by various things. You can think of them as being labeled by a maximal non-anomalous one-form subgroup of AG. So it's all the lines that are mutually local that can condense on the boundary, or equivalently Lagrangian subgroup, which is basically same data, but basically you're looking for lines that are bosonic and commute with each other as well, a maximal subset of these lines. And particularly for Dirac-Fitting theories, these are labeled by a subgroup of the group G and a two-pole cycle of that subgroup H, which is precisely the data that also labels the set of gap phases in 1+1D. So H is what captures the symmetry breaking from G to H, while nu is the topological twist that encodes whether the gap phase is an SPT or a trivially or a trivial phase with global symmetry, topologically trivial phase. So this sigma, basically the zero form symmetry has an action on all the line operators of the theory, but a boundary is basically a list of line operators that can end on the boundary, a boundary. So the action of the zero form symmetry on line operators induces the action of zero form symmetry on gap boundaries, which maps one boundary to another boundary. So that's why this is like a -1 form symmetry. Something that would be useful is to have a procedure to kind of construct a spin chain on the boundary that acts on a local Hilbert space or a Hilbert space that has a local tensor decomposition and captures the algebra of line operators. So to do that, let's put the theory on a semi-infinite cylinder. Now this is also so similar to what you asked, Lakshya. This is also, I'm actually only interested in the 1D boundary, but I think of it as boundary of a semi-infinite cylinder. But in the end, I'll just study the Hilbert space of the theory restricted to 1D and not worry about where it comes from. And that maps to well-known questions in condensed matter pertaining to Ising model, or very down to earth lattice model. So, but it's just a way to get there. So I can break the space of all these operators into three classes. One is the semi-infinite line that is W, labeled by some dion D. Then there's a line wrapping the non-contractible cycle, and then there are local operators or open operators with both ends on the boundary. The correlation functions or the commutation relations between these lines are basically encoded in local moves that are further encoded in this alpha G that we. In particular, there's so this line gamma, which wraps the cycle, commutes with all the local operators that act on the boundary. So the first thing we can do is, if we have a boundary Hilbert space, we can grade it by eigenspaces of gamma. And in particular, we can decompose it also in super selection sectors that carry the same label as the dions in the gauge theory. So this and this would have a very kind of concrete physical meaning, spin chain, in a minute. Further, these operators, which are the semi-infinite lines, act as they shift between sectors. So it just take a sector D prime maps to sector D prime by action of WD. Concretely, the Hilbert space can be or the spin chain can be read off by putting some regularization on the boundary. And what I do is I break the set of operators into two groups. One is the pure fluxes, and the other is the pure charges. And I put some kind of regularization on the boundary where there's like a alternating set of points where the fluxes and the charges are allowed to end. So the charges are only allowed to end on the blue points, while the fluxes can end on the red points. And there's an operator algebra that they satisfy. So for example, this S alpha, this on side J minus 1, has a non-trivial commutation relation with the SG at J and SG at J minus 1, and commutes with everything else. So this algebra can be implemented as on a spin chain. Further, the product of so gamma G, when pushed to the boundary, basically becomes a product of these local operators SG. Similarly, gamma alpha, product of S alphas. And notice that SG acts on a local site. So I label the sites by these blue points, while S alpha acts on between two sites. These operators, so in this kind of a construction, we can actually write down operators of finite length of any length, given length, and labeled by some dion D. And these operators have nice properties. They somehow know about the modular tensor category, which is natural because they are basically line operators in the bulk that have been pushed to the boundary. So
these operators defined by lines going from one point to another point, are they a choice of linear transformation from between the two vector spaces that you're making, or is it something canonical?
I'm not sure I understand your question. So what do you mean?
So at every point you have some Hilbert space, right, which is graded by these lines, the set of lines that you have. And then you also define an operator when there is a line connecting 2 points. Then you define an operator between the two Hilbert spaces.
So what I do is I know the algebra of SG J minus 1 and S alpha J plus 1. That's just coming from these rules.
Mm-hmm.
So then I know that I can diagonalize some subset of these. I can always choose to diagonalize the fluxes, for example. So I define local Hilbert space by eigenspaces of the flux, and then I use the charge operators as raising and lowering operators on these two. Mm-hmm. So that's the kind of thing I do concretely.
So at every point, your Hilbert space is it? Does it just the basis elements are comprised of the set of lines,
Yes.
or is it just graded by the set of lines?
So the basis is one-to-one correspondence with the set of fluxes, not all lines.
Okay.
And then I
Okay.
use the other operators, which are the charges, as raising and lowering operators in this finite dimensional Hilbert space.
Okay. Okay, I understand. Thank you.
So eventually what we end up with is some recipe to write down operators that are of finite length, n number of sites. And these operators are labeled by elements of the quantum double of G. And their commutation relations are basically related to the S matrix. There are other properties, for example, they can, if you take two of them on neighboring regions, you can extend them. And so using different computations, one can extract the S matrix and T matrix and fusion algebra, things like that of H theory, which is kind of expected because they're coming from the string operators in the bulk. So here's like a table of some operators of different finite groups. There's something that one needs to do is put some kind of a non-canonical ordering if you have a product of cyclic groups, and use that to define some kind of, so there's some details that go into defining these operators such that they satisfy the properties we want them to. So given all of this, there are now we can define spin chains that can access the full phase diagram. For example, if you want to construct so the commuting set of dions which describe a gap boundary can be used to construct a fixed point Hamiltonian for that particular gap phase. Just by taking the operators S that are carry the same labels as the things that condense, and adding arbitrary operators of arbitrary length with some arbitrary coefficients. For example, if we take some minimal model where we only take some operators that come from strings of length 1 within a Lagrangian subgroup, then that defines a simple translation invariant fixed point Hamiltonian that is within a gap phase labeled by the same subgroup and cocycle of the full group of G that labels that boundary. For example, and this construction also gives order parameters for different gap phases. So for example, kind of trivial way, there's the Hamiltonian labeled by these Ds. A product of Ds on the ground state of this Hamiltonian will have an eigenvalue 1. And this allows one to read off order parameters for different symmetry breaking or SPT phases. Further, all these operators, S's, since they commute with the gamma Ds, one can grade this Hamiltonian also by eigenspaces of gamma D and split it up into sectors. So something that will be useful is a general Hamiltonian then that can access different gap phases, so can at least have like some minimal understanding of the phase diagram, including the phase transitions, is just the sum of the Hamiltonians corresponding to each of the gap phases. And so something else that's useful is to look at twisted sectors, because what we eventually want is to see how one gap phase maps to another gap phase under a duality transformation, And that information would be encoded in how different twisted sectors, symmetry twisted sectors transform. The symmetry twisted Hamiltonian is basically defined as follows: as a symmetry operator in the spatial direction at some time, and a symmetry twist. So that the Hamiltonian is basically defined with some twisted boundary conditions. And we can also construct characters that are labeled by the same data as lines of the bulk theory. So this character is basically constructed from states that have a definite, that transform in some definite representation alpha and have twisted boundary conditions G. And so useful thing is that these characters, which are constructed within some region, some parameter space of the theory, map naturally under the duality mapping. So if I have some global symmetry of the bulk, let's say sigma, I can write down the theory. If for some parameter regime lambda, take sigma and get a dual character where D has been transformed to sigma D. And there's also an action of zero form symmetry on the parameters of the theory. So concretely what happens is there's a Hamiltonian. There are some parameters in this Hamiltonian lambda. If sigma transforms S's to sigma, D's to sigma D, and that induces a transformation on the parameters in the model. So we get some dual twisted character, which has the same spectrum as the original Hilbert. So there's a Hilbert space labeled by, there's a Hilbert space labeled by D, and in some parameter region lambda, and there's a dual Hilbert space labeled by sigma D in some dual region sigma lambda, and those two have the same spectrum. Those two. So let me look at some concrete example where this works. For Z2, where the group is Z2, the line operators are labeled by elements in Z2 times Z2, which is generated by the electric line and the magnetic line. The magnetic line is basically a group element. The electric line is a representation of Z2. And the zero form symmetry is just Z2, which exchanges these two axes up. EM duality, or there are two gap boundaries. One is the M boundary and the E boundary, where the M and E lines are allowed to end. And from the perspective of subgroups, the M gap boundary is labeled by the full group, while the E boundary is labeled by the trivial subgroup. And the effective spin chain for this is basically obtained by finding local Hilbert space on which there are these SM and SE operators. The SM operators act on site while SE act between two sites, and SE anti-commute with the two SMs at site J and J plus 1. So this algebra is realized in this by these Pauli operators X and Z. The electric line that goes between two sites, J and J plus 1, acts as ZJ plus 1, and the local operator, which is induced from the magnetic line, is just XJ. Of course, this is just the transverse field, the operators that enter in the transverse field Ising model. Similarly, one can take a string of electric operators, which just becomes sigma z's on the two ends, while a magnetic string becomes a product of sigma x's along the string. This Hamiltonian is well studied, has a C equal to half transition, and two sides of the transition are mapped to each other under Kramer-Warnier duality. And this can be read off directly by, for example, looking at characters that are labeled by representation of group elements. So for example, chi E is the character with a non-trivial representation of Z2. And so on. Chi M is the one with the symmetry twisted Hilbert space. And chi F has both the non-trivial representation as well as the symmetry twist. Now we know that under EM duality, chi of some D in this dion label set maps to chi of the EM dual dion, and the parameter lambda goes to 1 minus lambda. This written in terms of twisted partition functions has the familiar form of gauging Z2 zero form symmetry to get a dual Z2 zero form, which we know is Kramer-Vannier. Something else that can be done is we can take non-minimal extensions. So for example, instead of taking strings of length 1 and bringing them to the boundary, you can take longer strings and see what kind of a Hamiltonian is induced on the boundary. And this Hamiltonian also has an interesting phase diagram. It realizes tri-critical easing model, which has some relevant operator that can flow back to the easing fixed point. So this is mostly, so all of what I'm saying is actually already known. It's just offering a different perspective of how one can think of these different features arising. But this would be useful in looking at slightly more non-trivial examples. So if you look at Z2 times Z2, the lines are again labeled by, this should be Z2 squared times Z2 squared, sorry. And the zero form symmetry group is S3 times S3, a semi-direct Z2 of this theory. So it's a fairly large zero form symmetry group, and all the gap boundaries are connected under the action of the zero form symmetry. So there are 6 gap boundaries labeled by these generators. So these are the ions that can condense on each of these boundaries, and they're labeled by some subgroup of Z2 times Z2, as well as a co-cycle. So this is a non-trivial SPT, and this is a trivial SPT. So that the action of this S3 semi-direct Z2 on the gap boundaries is given by these generators. So there's some group element that maps, for example, the ferromagnet to the SPT, and everything else is left invariant under K3. In particular, the K. So what we can split the set of 6 gap phases into 3 subsets, on which there's an action of S3, and then there's some symmetry transformation, which is basically EM duality on the second layer. So it maps MR to ER and ER to MR, that maps between these triangles. So now what we can do is take some fixed point that we understand. For example, there's this fixed point that's just easing squared, comes from 2D. In the previous example, we saw EL transforming to ML. Sorry, the phase transition between EL and ML was given by easing. So here it's just 2 decoupled easing. But now there are zero form symmetries that map between this transition and any other transition in the theory, which can be used to understand what is the spectrum, for example, of the dual transition. So yes. Further, the Hamiltonians of that can be used to write down the operators used to write down the fixed point Hamiltonians can be constructed in a way similar to the one discussed a few minutes back. And for example, what one gets is is so for the SPT phase, string operators brought to the boundary become these kind of operators. Now, if I just take a product of these operators in some finite region, we get this kind of a string operator. And it's known that this is a string operator which is the order parameter for the SPT. So all the order parameters for the gap phases kind of naturally appear as representations of the string operators are allowed to end on that particular boundary. Something else that we can do is the spectrum of this CFT is known because the spectrum of the easing CFT is well understood in different Z2 twisted sectors. So what we can do is use that spectrum, map it to this transition here. So we know that, for example, K1 under K1, EL goes to ELMR, but EL is nothing but a Z2 odd Hilbert space of this theory. So it has some spectrum, which is given by chi1 16 squared and chi1. And what we could do is just use this duality mapping and study the spectrum of, for example, the transition between the two SPTs. So there's some prediction that one gets, which is essentially by the K1 map. So K1 maps ER to MLER. And the spectrum of MLER is known for the easing squared CFT. So that should be the spectrum of the CFT at this transition. So these are just orbifold CFTs that appear by this kind of duality mapping. And you can basically get all the different transitions in triangles, as well as the transitions between the vertices of these triangles. Something else that one gets for free in this approach is if you look at, for example, the transition between these two phases, which is given by this Hamiltonian here. It's also described by easing squared CFT, but this easing squared CFT has a marginal deformation, which basically goes up in this triangle, so that the marginal deformation is parameterized by lambda, and the operator that it corresponds to is basically given by the Hamiltonian that can be read off from this set of now in the so it's known that this line is basically the Ashkin-Teller line that's described by Z2 orbifold compact boson, some radius controlled by lambda. But so this immediately tells us that we can use the duality to get various other orbifold Z2 orbifold CFTs in this phase diagram. So basically, it's kind of just knowing one part and some symmetries allows a lot of quick tricks, which otherwise would either require a lot of numerics or require some kind of more sophisticated analytical tools, but somehow cheap way to get a lot of stuff. Also, finally, I spoke about these non-minimal extensions of the Z2 theory, which were basically generated by some strings in the bulk of length with greater than 1. And those non-minimal extensions basically allowed one to access some tricritical easing point. in the context of the Z2 on spin chain. Now for the Z2 times Z2 spin chain, we can do the same thing, but what you get is tricritical easing squared, and then we can dualize that. So there are all these interesting transitions which appear as deformations of this transition between the two SPTs. So here there's like a two-dimensional parameter space labeled by lambda1 and lambda2, which allow to access some non-minimal extensions easing model that have transitions that are in a universality class that are obtained by orbifolding two decoupled copies of the tricritical easing model. Yeah. So finally, I'd like to finish off with mentioning a few directions in which we could go with this. One thing that's interesting is that we could look at transitions between two SPTs that are not from the same, that are not protected by the same group. So typically, conventional phase transitions happen between they're like order disorder transitions where one side of the transition is necessarily a subgroup of the other side. But here there are two distinct groups and two distinct topological twists. This sounds unconventional, but in this approach, it comes out everything comes out on the same footing. So it's nice that it happens like that. Finally, in higher dimensions, there could also be transitions that can be accessed between topologically ordered phases and conventionally ordered phases by viewing one form symmetry as some topological order, symmetry breaking as a topological order. Also, it's tempting to ask what happens with more general symmetry structures, higher groups and categorical symmetry and so on. Yeah. And there's also a puzzle about if you have a zero form symmetry, so if a transition is invariant under some duality, for example, the Kramer-Vanier fixed the easing CFT is self-dual under the Z2EM duality of the bulk. What can we understand about the operator content of this transition from the fusion category that one gets by gauging the symmetry in the bulk? At least for the easing, they turn out to be the same. There's an easing CFT in the boundary, and if we gauge EM duality, we get easing fusion category in the bulk. But more generally, the connection is not hasn't been worked out. Yeah. So, thank you.
Great, thanks a lot. Let's thank Apoorv for his really nice talk. Are there any questions? So maybe we can go back to the slide before where you had the tricritical easing model. So I guess that's tricritical easing squared on the left, right? Where the blue dot is.
Yes.
And then, so there are these two parameters, but can you also then generate new theories in this way, like new fixed points that were not known?
So I think the minimal fixed points are the blue, these ones.
These light blue ones.
Yes, but deformations of this point could access. So by deforming this point on the parameter space, we could access some fixed points that are more interesting. For example, the tricritical easing squared. Mm-hmm. But these but knowing that the same or related criticalities would be in the vicinity of this this point in parameter space is not obvious just by looking at the Hamiltonians. But these dualities allow us to predict the existence of some criticality and also pin down the spectrum of that criticality. Things like that.
Very nice.
And also it tells us actually the point where to find that in parameter space, because there's a mapping of.
Jingzhang, do you have a question?
Yes. Can you say a bit more about the deconfined criticality? Like, how do you consider that in this bulk perspective?
Yeah.
Like where I have two different groups on two sides of the critical point.
So it basically would involve. So if you have a bigger group, so here I only gave a simple example of Z2 times Z2, but if there's some bigger group that has several subgroups that can admit non-trivial 2 co-cycle, as well as duality map between, so let's say you have 4 gap phases, 1, 2, 3, 4, and 3 and 4 are these ones that have a non-trivial co-cycle and different groups, right? And 1 and 2 are some simple gap boundaries. For example, all the charges condense in one and all the fluxes condense in the other. So everything is known about the transition between 1 and 2, but the transitions between 3 and 4 might be not so well understood. Now, if you find some symmetry that maps the set of condensed operators on 1 and 2 to the set of condensed operators to 3 and 4, then that entire phase, the region of phase space that's understood maps. So there are various things that can be predicted and checked. And the simplest group where that happens might be Z2 cube already.
Okay, any other questions? If not, we can actually stop the recording and then have a more informal discussion. So let's thank Apoorv again for this very nice talk. I stopped mine. Laksha, can